Every intelligence, artificial or biological, solves a fundamental optimization problem, minimizing the distance between current prediction and objective reality. The gradient is a vector field representing the direction of steepest ascent. By taking its negative, we identify the most efficient path toward a local minimum. In a neural network, this surface exists in a space with millions of dimensions, where each coordinate is a synaptic weight or bias subject to adjustment. We quantify failure using a loss function, such as mean squared error. This scalar value maps the network performance to a single point on our terrain. To compute the gradient, we calculate partial derivatives for every weight. This tells us how a tiny change in one specific connection affects the total error. The chain rule allows these error signals to flow backward from the output layer to the input. We multiply local gradients to find global impact. The learning rate, denoted as alpha, scales the gradient. It determines the size of the step we take toward the minimum during each iteration. If alpha is too large, the system overshoots the minimum and diverges. The loss increases exponentially as the updates become increasingly unstable and chaotic.
Conversely, a rate that is too small leads to plateaus. In deep architectures, gradients can vanish, becoming so small that learning effectively stops altogether. Standard gradient descent uses the entire dataset for one update. Stochastic gradient descent uses a single random sample, introducing noise that helps escape local minima. Momentum optimization adds a fraction of the previous update to the current one. This simulates physical inertia, allowing the descent to accelerate through flat regions. Modern optimizers like Atom adjust the learning rate for each individual parameter. They track both the mean and uncentered variance of past gradients.
In high dimensions, local minima are rare. The real challenge is saddle points, where the gradient is zero, but we are not at a global minimum. Convergence is reached when the gradient approaches zero. The network has now found a set of weights that generalize patterns from training data to reality.